All right, so it turns out that you'll see in your book names of lots of different graphs, but it turns out that all those different graphs with different names are really very similar in idea to this histogram. So it's basically a histogram with minor variations. So now let's talk about these variations of histograms. But before we do that, let's say that we have this histogram of the original distribution. And let's say that right now, on the y-axis here, I chose to represent how often the values occurs as a frequency or as just a raw count. But we said before that you can have a distribution where you chose to represent how often the values occurs as a percentage instead of as a frequency. So if we had changed these frequencies as percentages instead, then do you think that the overall shape of the distribution, does it stay the same or is it different? So again, this distribution, if I had represented it instead of frequencies, on the y-axis here, I chose to use percentages instead. Then does the overall shape of this distribution, is it the same or different?
This is the same.
Yeah, why is this the same?
Because the ratio of the frequencies as bar numbers and as percentages is the same.
Yeah, excellent. So it does stay the same, and again, the reason is, when we say the overall shape, what we mean is the relative shape. That means that this, this bar here is twice as high as the bar that's next to it, and the last bar is 3 times as high as the second bar, and so on. So that's the relative shape. So the relative shape stays exactly the same if you chose to represent these as percentages instead. And the reason for that is because the only thing that changes if you change this 1 instead of a percentage is we said that you divide by a constant number, in this case 6. So all you would do is take this 1, divide by 6, and that becomes a new number. That's 16.6%. You take this 2, divide by 6, this becomes a new number, 33.3%. And this 3 divided by 6 is a new number, 50%. So to convert this frequency distribution to a relative distribution, all we're doing is relabeling the y-axis, and the picture actually stays the same. So the point of that is that throughout this class, I might draw out some distributions, and there might be a variable here for x, but sometimes I won't label the y-axis. And the reason for that is the y-axis just represents how often each value occurs, but it could be a frequency, it could be a percentage, it doesn't matter. And so that's why we can get away with not labeling the y-axis, because the general shape is still the same. Any questions? All right, so now that we talked about what a histogram is, which is a bar graph that represents a distribution, let's now talk about variations of histograms that has minor differences, but the overall goal of the graph is the same, which is to relate possible values of a variable with how often each one occurs in the data set. So one variation of a histogram is called a dot plot. So instead of the original histogram where we have a bar of a certain height, we just use the appropriate number of dots. So that's all it is. So this is a dot plot. It's conveying the same information that a histogram would. But what do you think advantages or disadvantages of a dot plot might be over the original histogram?
I lost it, I'm sorry.
That's all right. You ready? Yeah.
It may be easier to count how many of each one is without relying on the y-axis.
Yeah, so typically, with a bar, you'd have to align your eye to the height of the bar to see what the actual reading is, right? But if you have a smallish number of points, then you can see the actual number, or at least the relative number, without having to align your eye to the axis. So that's one reason. That's in terms of interpreting the dot plot. But what about in terms of actually constructing the dot plot? Nowadays we have computers that do all this, but let's say that you were constructing the dot plot by hand. Then do you think it would be easier or harder, faster or slower to complete, to draw out the dot plot versus the histogram?
Generally, it'll take a lot more time to complete a dot plot because you have to, again, make every single dot for every single point, which makes larger numbers completely infeasible.
Okay. What other comments you guys have?
Yeah, it makes it easier and faster since you don't have to like color in every single thing. And it's just quick like dot instead of having to make multiple lines or fill in anything.
Okay, so.
I think it depends on like how big your number is. If it's like smaller numbers, you'll probably do the dot plot, but if it's bigger, you can just do,
Depends on the data set, okay?
Yeah.
Anybody else want to add to that? Okay, so let me try to answer the question by building up to it. So let's say that you had the original histogram where you have bars of a certain height. Let's say that you wanted to know how high you should make the bar that corresponds to the 70s. So how many times would you have to go through your data set to count the number of instances that match that group? So if you want to find how high the bar for the 70s should be, going through your data set, how many passes through your data set would you have to make? How many comparisons with the data points? So in other words, if I wanted to know how high the bar for my 70s should be, I have to go through my data set and I say, does this belong in the 70s? Yes. Does this belong in the 70s? Yes. And then does this belong in the 70s? No. So I would have to make 6 comparisons in order to decide how high the bar for my 70s would be. And then I'd have to go through and count the check marks. So that would be 2. So then just to find the bar, the height of the bar for the 70s, I'd have to make a comparison for each data point in the data set. So I'd have to go through and make 6 comparisons because there's 6 data points here in the data set. So I'd have to pass through my data set, all of the data points in my data set once in order to know how high the bar for the 70s should be. What about the bar for the 80s? I would basically need to do the same thing. I'd have to now go through again and ask, does this belong in the 80s? Does this? And then go through and make all the comparisons, and now I have to make 6 comparisons and go through that entire data set again. And then, so I would have to do that for basically all the groups here. So how many groups are there? There's about 10 groups. So basically I have to make, go through the entire data set 10 times just to know the height of each bar. For a dot plot, how many comparisons do you think we'd have to go through?
6.
Yeah, so only 6, passing the data set only once. And why is that? Because every time you look at a data point, you can just mark it once in the group that corresponds to. So at the 70s, you make a dot. And then you go through the next point in your data set, another 70, or another point in the 70s, you make another dot in the same group, and so on. So you go through every data point exactly once to make the appropriate dot in the plot. And so because of that, you only have to go through your data set once. Versus a histogram, you have to go through your data set the number of times it corresponds to your group. And then at this point, you might be asking, well, that's because we're constructing this by hand, but who does that anymore? It turns out that you'll notice, even if you do this on a computer with a large number of data points, you'll notice that the computer takes noticeably longer for a histogram versus a dot plot. Because internally, this is what needs to be done. Any questions? Okay, so like if you have millions and billions of data points, for example, it would take a computer noticeably longer. Okay, so let's look at the next variation of a histogram, which is stem and leaf plot. So in a stem and leaf plot, the first difference is, we said before that this x-axis, the axis of the actual values, can be labeled either at the boundaries, which we ended up doing, or they can be labeled for the entire group. So in a sum and leaf plot, we're gonna label the entire group, and we're gonna label basically the most significant value of the data points. So the leftmost value is the most significant. This is the 70s, and then this extra value is fine tuning it, and this is less significant. So in the sum and leaf plot, we're going to label the most significant value for the group. So this will start out at the zeros, and then the 10s, and the 20s, 30s, 40s. And we're just going to label them as a single number. So because this last group includes both the 90s and 100, we're going to say this is, so we'll say 9. If we want 100, well, we'll talk about doing that in a moment. So we're labeling the entire group, and then we go through our data set, and then let's say we have a 73. What we would do is we would go to the column that contains the 70s, which is notated with 7 here, and then we would put a 3 there. So this corresponds to a data point that represents the number 73. And so same thing here, 77, we would go to where the 7s are and put a 7 there. This represents a data point of 77. And we would do the same thing to all the other data points. This 82 here would correspond to the 80s, and then we would put a 2 there to indicate that data point.
That must mean this is for really small samples, right? Because the bigger you go, the more and more numbers you're gonna get.
Well, they pertain to large ones too, but the smaller ones, it's easier to do by hand. But this is just showing you that if you were to do it by hand, then yeah, it would be a small data set. But large data sets can be done in the same way, but with computers or calculators. So here, the 94, what would that look like? It would look like the 9 here, and then you go up and put a 4 there for that data point. Okay, and then the 95 would be there's a 5 where the 9 is, and then the 97, there's a 7 where the 9 is. So this is very similar to a dot plot, but instead of dots, you have specific numbers. So what do you think the advantage of this over a dot plot is?
You don't have to count the specifics.
Yeah, you can immediately look at it and tell what the data point is. It's not just a dot. Okay. So why do you think it's called a stem and leaf plot?
The numbers at the bottom are the stems, and then the numbers in the center are the leaves of each.
Okay, very good. So this is an analogy from plants. So in a plant, you've got the trunk of the tree or the plant, and then it branches out. So as it's branching out, this would be the stem. And as it becomes less and less significant, these would be the leaves of each of the stems. So each of this would be the leaves. And so each number here on the x-axis, this would be the stem. And as it's branching out, becoming less and less significant in the numbers, then these would be the individual leaves. So here we chose to represent the stem and leaf plot where the stem is on the x-axis and the leaves are growing up vertically. But you can easily imagine this same idea but rotated so that the stem is maybe on the y-axis and it's going out horizontally, and you very well also see that as well. Any questions? Okay, so in this case, the stem and leaf plot, the y-axis wouldn't even be labeled. All right. So moving forward, the next variation of, before we move on. So in a stem and leaf plot, of course, because you can tell the value of every single data point, if you have duplicate values in your data set, you would also be able to see that too. For example, if we had 277s here, then you would just have another data point that corresponds to the same value. So if you have duplicate data points, you can also see that in your stem and leaf plot. All right, so let's talk about the next variation of a histogram. This is called a frequency polygon. So a frequency polygon has a very complicated name for something that is very simple. So if we go back to the original histogram, and let's say that we chose to label our x-axis where the groups are, and so this would be the 0s, the 10s, the 20s, 30s, and so forth. So if we have the original histogram, we would label the heights of where the bars are at the midpoints of the groups. And then of course, the ones that have a height that have 0 representation technically have a height of 0. And then where all those dots are that indicate the height of the bars of each group, those are just connected with line segments. So that would be so in a frequency polygon, this red line graph is the actual frequency polygon. And you can ignore the underlying black bar graph. Yeah.
Can I get some water?
Sure. Okay, any questions? All right, so the next example of a variation of a histogram that we'll talk about is a Pareto chart. P is actually capitalized because it's named after somebody. So Pareto chart. So all a Pareto chart is imagine the original histogram, the original bar graph.
What are the dots on top of the bar?
Oh, the dots represent the heights of each of the bars, but at the midpoints of those bars.
Oh,
So then those are the dots, and then we just connect those dots with line segments. So a Pareto chart is just, you look at the original histogram with the bars, and then you arrange those bars in order, in descending order from tallest to shortest. in this case, you notice that the tallest bar occurs at the 90s, and then the 70s, and then the 80s. So we're just gonna basically rearrange that in this graph to reflect that. So basically that involves having to relabel this x-axis. So that's gonna be here, the 90s versus the 70s versus the 80s. So the 90s had a height of 3, and then the 70s had a height of 2, 80s had a height of 1, and then everything else had a height of 0. So then you can just label those in any arbitrary order, but we can go in the order of where it was originally in the table. So we'll do, here it'll be the 0s, and then the 10s, and the 20s, 30s, 40s, 50s, 60s. So this is a proto chart. It's nothing more than the original histogram, but sorted in descending order of height. So let's talk about when this might be relevant. So let's say that you're interested in answering the question of what contributes the most to happiness. And then you go out, you ask a bunch of people what, how they would respond to that. And so let's say that you then collect the answers in a pie chart. So you ask, what contributes the most to happiness? And let's say a lot of people say family. And then there's gonna be a lot of people who say friends. And then let's say pets. And then some people say sports, and then some people say music, and then some people say TV, for example, and then some people say food, and then some people say sleep, and so on. So do you think this is a good way to organize that data? And again, this is answering the question, for example, of what contributes the most to happiness. And let's say we had organized this data in a pie chart. Do you think this is a good way to organize the data? Yeah.
Without knowing the specific percentages, it's kind of difficult to tell which is more than the other.
Okay, very good. So the percentages, the actual numbers are missing, but let's say that we put those numbers in later. Even with the numbers, do you think this would be a good visualization? Because in a visualization, you want the reader to be able to immediately capture the point of the picture, the essence, in as little effort as possible. You don't want them to have to sit there and scrutinize numbers. So just in terms of visually, do you think that this is impactful and able to convey the information quickly? Yeah, why is that?
Because generally larger data sets are represented in a larger word, a larger chunk of the actual visualization, which immediately conveys to the reader what is the main points, and it's also just a pleasant visual that simultaneously communicates what it's trying to put out.
Okay, good. So in this case, for example, if you have categories that are very similar in quantity, similar in area here, like pets and sports, it's very hard to tell how much of a difference these are, or the difference between pets and TV, just how much of a difference that is. So if you were to organize this exact same data as a Pareto chart, for example, where you basically have a bar graph and they're organized in descending order, then you might have something like this, where now family is here, and then let's say friends is here, and let's say pets is here, and sports is here. So now just by looking at this, it's very easy to tell the relative relationships between the categories. So this Pareto chart does a much better job in visualizing in this example than a pie chart would. Any questions? Okay, so the point is that these are all examples of tables and graphs, which all have different complicated sounding names, but keep in mind that they're all achieving the same fundamental purpose of a histogram would, which is to show the relationship between all values of the variable and how often they occur in the data set. So they're all doing the same thing, but in very slightly different ways. Okay, so now that we talked about what a distribution was, and variations of distributions,